Okay, so we're going to make the transition into Chapter 20. And Chapter 20 has sort of two new functional groups, almost three when we consider it naming, even though the third one really isn't considered usually a functional group. It has enough differences in the physical and chemical properties of it that we can kind of think about it. And so what we're going to do is we're going to introduce alkenes. And notice that the endings are changing, and they're sometimes only changing by a single letter from alkane to alkene. That means we go from talking about carbon-carbon single bonds to something that has a carbon-carbon double bond in it. And then we can have alkynes, and so that Y indicates that my molecule has at least one carbon-carbon triple bond. And then we'll talk about aromatics that have that special functional group where they've got a six-membered ring that has alternating carbon-carbon double bonds. And so it's not really a new functional group, meaning it's just carbon-carbon double bonds and it's just folded around into a ring, but that ring has some pretty unique physical and chemical properties that make it useful biologically as a building block, and also just make it much different than compounds that have just regular carbon-carbon double bonds in them. The ending for a double bond is an ENE, obviously, and the ending for a triple bond is YNE, and then we're going to do this tomorrow. And tomorrow doesn't have two M's. I don't really care, but anyway, the rules for aromatics are kind of separate and special and are covered, in their own day, so as to sort of not overload us with the double and triple bonds. And so we'll be covering that, I guess, on Friday. And with the advent of these new functional groups, we have a couple new rules that we have to realize. The first one is that we always give the functional group the lowest possible number. And then, of course, we always have to tell where the functional group is. Oops. Oh, don't mess up on me already. Really? It's just going to be one of them days, huh? Do you remember first semester, the good old days when the programs didn't lock up and everything was just hunky-dory? Now we got computer programs locking up left and right. Cats and dogs. It's raining frogs. I don't know. Did everyone kind of get both those sentences down? Good enough. I'll put both. So, yeah, so longest chain, or the longest chain is numbered to give the functional group the lowest number. And we have to number the functional group, or we have to give the location of the functional group. And so kind of an example illustrating that is, if I have this molecule right here, if I have a chlorine on this side and a carbon-carbon double bond on that side, the carbon-carbon double bond, actually, let me even make it better. We'll put it right here. The carbon-carbon double bond always gets the smallest number. So in the past, if we had, say, a chlorine on the end, we'd start numbering from that end because that would give a functional group with the number 1, right? But now the functional group always gets the smallest number. So in order to give that double bond the smallest number, I have to start numbering that way. Because if I choose the way in red, then my functional group is on the third carbon, whereas in blue, it's on the first carbon. And so the blue is the correct numbering. And so we would call this 5-chloro. So we still put our side chains first, and we still put them in alphabetical order like always. And then we have to tell the location of that carbon-carbon double bond, so that's 5-chloro, 2-pent-ene. So that ene ending is changing from an A and A to indicate that double bond. And the 2 is telling me where that double bond starts. So we automatically know that if it starts at 2, that it goes between 2 and 3. If it starts at 1, it goes between 1 and 2. So we don't have to give both ends of it or anything. And then, of course, the 5-chloro is like normal, kind of. So, actually, let's do this. We'll make it really interesting. What would we name that one? Start from the left or the right? Yeah, we have to start here because that gives that double bond the lowest number again. And then what do we have to remember about chloros and bromos? Yeah, we have to name the bromo first. Then we name both chlorines, so we remember to throw that di in there. And then we've got 2-pentene. Okay, what if I do this? Now, one of the ways I'm making it more difficult is to simply throw in a lot more functional groups in my molecule so that we have to keep track of the alphabetical order and stuff. And that's kind of what I do on a test. I just add lots of functional groups. Left or right end again? Okay. Maybe I'll have to make one start on the left end. So I've got 7 carbons in my main chain. And why did I start on the right end instead of the left end? Yeah, so even though if I started on the left, I'd end up with like a 2,2-dimethyl here, because we want the functional group to have the lowest number, I've got to start on the right side, even though the other way gives me more smaller numbers. And then let's see, I've got some ethyls, methyls, and bromines. What comes first? So I've got a 4-bromo. What's next, ethyl or methyl? Ethyl. Why doesn't the dimethyl come first? But D is before E. Yeah, the dis and tris don't count, remember. So 5-ethyl dash 6,6-dimethyl. And so when we're looking at alphabet, we're looking at the M, the E, and the B. We ignore that di part. Dash 2-heptyne with a Y and E ending. Now I should point out one thing with the triple bonds that's different from the way I tend to draw them, because I draw them as an afterthought usually to the molecule. But from when we were making molecular models like that, what do you remember about the shape of a triple bond? So I draw them like this because I don't think about it ahead of time. What do we really know about a triple bond? In fact, I can even make one. Yeah, it's linear, right? And so what the computer tends to draw is it draws it like this. And then it doesn't put the dots in, but it'll draw it as a straight line part of the molecule. And so you get molecules that look like, you know, where I'll draw this like that, it'll draw it, it'll get the diagonal part, and then because that part is linear with the triple bond, it'll draw it like that, and then that's linear, and then it'll go like that, or something. And so the way the computer draws them and the way I draw them is a little bit different. Just remember that it really means there's a carbon on both sides of that triple part when it's drawing it. And you'll get practice because you'll have the homework, you'll have lots of extra practice sheets and things like that. So I think you guys will get used to it. Let's see, what can we do to make things harder? Ah, here's a tricky one. Where do we start numbering on this chain? I have to start numbering on the functional group, right? So notice that that goes 1, 2, 3, 4, 5, 6, even though if I numbered it starting at one end of the molecule, 1, 2, 3, 4, 5, 6, 7, I'd actually get a longer molecule just labeling just the longest carbon chain, right? But remember, that chain has to include that functional group. And so sometimes now our longest chain isn't really the longest chain. Now we have to be sure and phrase it and say, what's the longest chain with the functional group? So this would be 2-ethyl, because I've got a little ethyl group here, dash 1 hexene, since it's just a double bond. Okay, let's add some more things that may or may not be tricky. It's not only tricky because you haven't gotten it yet. What if I have more than one double bond in a molecule? Yep, so this we're going to number 1, 2, 3, 4, 5. And this is going to be 1, 3 penta. And the part that you might not know is where that di gets stuck, but the di gets stuck right before the E, because it would be really weird to say 1, 3 dipenta, because that wouldn't make much sense. That would sort of indicate that there's something, 2 of something with 5 chains, right? But the part that there's 2 of is the E part, and so this is 1, 3 pentadiene. And so, like I said, all the same kind of rules are there. It's just we're modifying them a little bit. You know, we're used to dimethyls, trimethyls, things like that. Now we have to realize that we can have more than one functional group, and that di part goes with the functional group part. What if I get really wacky and I have a molecule with a double and a triple bond? You know, that's perfectly logical, Brittany, and every year someone says that, and I have no idea. This is one of those, I just throw my hands up and say it's retarded, but that's the way the rules work. If there's a tie between a double and a triple bond, the double bond wins. I don't know why. I don't make up this shit. It's just the way it is. Although, frankly, for all you guys know, I do make this stuff up. I've thought about making my own naming rules and stuff up different every year. It'd be kind of funny. You know, people would like answer last year's homework with last year's naming rules, and then this year's naming rules, I'd just change them up, and so they'd be all wrong, put different endings on. It'd be hilarious. So let's see, we got 1, 2, 3, 4, 5, 6, 7. So this is going to be 1 heptene dash 6 ine. And so notice that where we put the numbers kind of is weird too, in that we put a number right by the functional group at the end. So it's an E9 actually. And you might see them numbered differently occasionally, in that sometimes they'll call, you might see this as hept 1 ine 6, ene 6 ine. And that's the new naming rules, but since your book goes by the old ones, we're going to stick with the old ones. But I do want you to realize that if you see something a little bit different on a website somewhere, or if you're looking something up with Google, that, you know, those little differences are because some people use the older set of naming rules and some people use the newer set of naming rules. So when there's a tie, the carbon-carbon double bond is more important than the carbon-carbon triple bond. And so we give this the lowest number. Now remember, that's only if there's a tie. If I have a molecule like this, where the double bond is in the middle of the molecule, then I really am going to name it that, I'm pretty sure. And so we would call this 3-hexene-1-ine. I wouldn't worry too much about the little fringe cases. I usually don't put a ton of those on the test. Although, you know, if you're aiming for 100% or 99 or something like that, you'll have to get those. Okay, so I've been throwing some difficulties at you, meaning we looked at what happens if I have two of the same type of functional group in there, and that's like a diene or a diene. We've now said, what if I have a double bond and a triple bond together? Can you think of another difficulty I could throw at you, just to keep life interesting and fun? Yeah, but that's not going to change the naming because those are side chains. So they're the lowest precedence. They don't change anything. Think back to your first homework. What's the type of questions that we had? Yeah. So we can look at cyclo. And so this molecule is cyclopentene. And we don't need a number for cyclopentene because it doesn't matter where I draw that double bond, meaning that all of these molecules are the same, no matter where that double bond is, right? And I could keep drawing ones where the double bond moves around. All of those are going to be the same. Where I need to start remembering the numbering is the second I throw a functional group on there. For instance, where does the 1 start in this molecule? I've got bottom left, bottom right, top right, and kind of the middle top. I'm going to go with bottom left because we have to number our longest chain going across the double bond. And so 1, 2, 3 gives me my lowest set of numbers, whereas I can't do this. I can't go 1, 2 because the 2 has to be in this direction. So I can't go around that way. And so we would call this 3-methyl-1 cyclopentene. Actually, we don't even need the 1 in there in this case. Cyclopentene. You know, it's one of those redundancies that sometimes I don't mark off, but technically, since it's not required, since it's implied that it's at the 1 spot, then no, we don't need it. Now, if I have more than one set of double bonds in a molecule, if I go like this, and I throw a methyl group in there, then I do have to do it. And so, you know, if I number this 1, 2, 3, 4, 5, 6, this is 5-methyl dash 1, 3 cyclohexadiene. Oops, I ran out of room. So the di tells me there's 2 double bonds. They tell me that they start on the 1 and 3 carbons, and that there's a methyl group on the number 5. Okay, there's one last trick that we kind of throw at you that we, probably 1 or 2 of the examples I gave you is actually technically a small amount wrong, mostly because I don't pay attention to it and I always forget about it at the end. And that's the fact that if I have a carbon-carbon double bond like this, I can now have a new set of things called SIS Trans Isomers. They're molecules that have the same formula, they have the same structure, meaning the way things are connected together are the same, but they have different geometry around those atoms. And you've already seen some examples of this because you've already seen or done these in both of our labs that I had you do. And so the easiest example to draw for that is this one where I have a carbon-carbon double bond, and say I have a chlorine up and a chlorine up and then a methyl group down and a methyl group down. Or I can draw them with one chlorine up and one chlorine down and a methyl group like this and a methyl group like this. Actually, yeah, I'll do it that way. Even though I used hydrogens on my examples, you'll be able to see the difference. And really, there's one more structure if you guys remember right. Do you remember what it is? It's if I put, say, both chlorines on the same side. And so if I look at it, these two are cis trans isomers, meaning they have the same structure, meaning it's carbon, carbon, carbon double bond, and then a carbon, meaning that it's 4 carbons in a row. Notice that, does the one on the right have 4 carbons in a row? So notice like this goes 1, 2, 3, 4. 1, 2, 3, 4. But this goes 1, 2, 3 for the main chain. And actually, I guess really if I'm counting, be honest, Jay, it should go 1, 2, 3. And so notice that even though I've drawn 3 models, the 2 on the left are cis trans isomers. All 3 would be considered structural isomers. And so notice that that last statement is what makes a cis trans isomer, meaning it has to have the different geometry. If it has a different structure, then that makes it just a structural isomer, because it has to have the same structure to be a cis trans one. You guys kind of clear on that or not? It's a little tricky. And then what we have to do is we have to have rules for naming these. So notice that both of these are 2, 3, dichloro dash 2 butene, right? And so notice that the one on the left we're going to call cis, and the one on the right we're going to call trans 2, 3 dichloro 2 butene. And so whether the chain kind of bends down in both spots or the chain kind of zigzags in both spots makes it cis or trans. And the reason I say you have to be careful is that every time you draw a molecule with a carbon-carbon double bond, there's potentially a cis and a trans isomer of it. And by default, when we draw the zigzags, we tend to draw the trans isomer. And so, you know, sometimes we forget to throw that into a name. And then just for completeness sakes, let's see, if we named this last one, it would be 1,1-dichloro dash 2-methyl dash 1-propene. And so notice it doesn't get a cis and a trans in it at all. The other thing to notice about cis and trans is that the parts on the same side of the carbon-carbon double bond have to be the different, meaning that it has to be a chlorine and a CH3 in order to be a cis trans molecule. Erin.
Would that do one protein or protein, or is it just, is there not a one?
Well, I put the 1 here, right?
So what was the difference between that one and the this cycle you don't put one?
Yeah, cyclo implies it. See, I could draw that. Well, I have to check. Maybe I couldn't. If I draw that like that, and I put a chlorine, and there's a double bond here, and a methyl, then we'd start numbering from this side. And so which side we put the double bond on matters, so we have to show the side. Yeah, you know, you might be able to leave the number out on that one. That's one of those, I got to be honest, there's a kind of a little bit of a gray area when you get to naming more and more complicated molecules. I personally feel that we should always put the number in because it doesn't hurt. That's what pisses me off about the rules sometimes. They're like, well, if it's obvious. Well, it ain't obvious. It's a lot easier to just throw the damn number in than not worry about it. I'm okay with, me personally would be okay with 1 cyclopentene. That's okay. But the real rule is that it's cyclopentene.
So for those molecules, we should put the number, but for the cycle, we shouldn't?
Yeah.
Okay.
Just.
Wouldn't that be drawn on because you've got 1 carbon?
Oops.
Carbon.
I'm sorry, the methyl group is on this one, right?
But then you have that double bond would be on one of those side chains.
Well, what I'm saying is that, see, the double bond could be here or the double bond could be here, right? So I'm not saying those are the 2 molecules. I'm drawing the alternate one,
Okay.
saying that because there's a choice where we put the double bond, then we have to give it its numbers. Although arguably it's always going to be on the 1 carbon in a 3 thing, so we probably could leave that off. I'm not going to, I'll be honest, if it's that cloudy of a case, I don't tend to take a point off. And it's only if you do it consistently wrong that I really get mad. Just like I haven't taken off points for forgetting to put the stinking dashes and commas in, right? Even though I should be. On some people, not everyone. Some people are pretty good at remembering them. Some people not so good. Let's see. So if I draw this molecule like this versus, oops, like that, that technically is 2 different molecules now, if we kind of think about it as cis trans, right? So here, what I'm saying is 1 hydrogen is pointing up and 1 hydrogen is pointing down. This is trans to butene, whereas this, because it goes 1, 2, 3, 4, this is cis to butene. Does that make sense?
Can you explain the trans and cis?
So trans means that when I draw it, one of the methyls is down and one part of the main chain is going up. And a cis molecule has both on the same side of that carbon-carbon double bond. So here there have to be both on the top, or equally well I can draw it with them down like this. Meaning these are the same molecule. Whether I draw it like that or I draw both parts pointing down, that's the same molecule. Because remember, I can always take and draw it this way, right? With the greens up, or I can draw it this way with the greens down, but up and down are the same molecule, right? Whereas if I draw one up and one down, there's no way to make those overlap. So one of the things we always have to have in the back of our mind when we draw a carbon-carbon double bond is always think, can it be cis and trans? For example, I've got those 2 molecules. What about this? Is that a cis or a trans? It's neither. Because if I drew it like this, say, it might make it easier to see. That's just a hydrogen, right? Meaning, notice I could make the longest chain go like that, in which case it kind of looks like trans, right? I could make the longest chain go like this, in which it kind of looks like cis. And since I can do both, it's neither cis nor trans. In fact, we would simply name this 2, let's see, 1, 2, 3, 4, 2-methyl dash 2-butene. And so what I'm trying to say is that if I've got, say, the 2 green ones on the same side of the molecule, meaning I have 2 of the same groups on one side of a molecule, then there is no cis and trans version of it. It's just the single molecule. Because, and we'll make it a little more obvious, I'll use the green ones. So notice with this green, the way I've got it drawn on the board, it looks like this, right? My finger stuck in the double bond. Here's the 2 greens, here's that other one, right? Those are the methyl groups. And so notice I could go like this, or I could go like this, but that molecule is the same as if I flip it upside down, rotate it left and right, and things like that, meaning it's always kind of got the same orientations no matter what I do. And so if I've got two of the same functional group on the same side, I don't have cis and trans isomers. So maybe we should just summarize this. Cis and trans, it has to have the same formula, meaning, you know, oh, wonderful, I crashed it. I don't know why I'm trying to break it. My other computer crashes even more often. Okay, so to summarize, well, maybe not. Well, didn't actually turn the pen on. Okay, we're getting there. For cis and trans isomers, we have to have that same formula. And what that means is that, you know, the CX, HN, whatever part has to be the same. And we have to have the same structure, but with different geometry. And really, we should also point out that it implies that we have to have a carbon-carbon double bond, because that's the only bond that allows us to have that different geometry like this. If I put a triple bond in, that's linear, right? And so that doesn't have different geometry at all, because it looks the same on both sides no matter what you do. And it implies that we have to have different groups on each side. And here's where it's a little hard to phrase that. What I'm saying is that X and Y have to be different. That if it's two X's on the same side or two Y's on the same side, then there would be no cis or trans isomers. Right, that's why I said that, you know, this is the technical description of it. This is what it really means. Meaning the technical definition is, you know, a molecule that has the same chemical formula, the same physical structure, but a different geometry around one atom. What that implies is that you have to have a carbon-carbon double bond, because that's the only case you can come up with it. Because remember, single bonds allow you to rotate around them, right? So you can't have a different geometry, because you can just change the geometry by rotating the bond. Triple bonds, since they're linear, since they look like this, even if I have different things on each side, it's still linear. It's not, there's not one orientation that's up and one orientation that's down. So triple bonds can't do it. And so really the only cis and trans isomers you can have are things with carbon-carbon double bonds. And because they have to be different geometries, that implies that I can't have two of the same things. Because if I have something like this, where I have two X's, then that implies, like this picture here, where it doesn't matter whether I draw it like this or like this, it's the same. But if I have an X and a Y on one side, then that makes this side different, right? And so it does matter whether I draw it up or down compared to the other side, because I can draw both up or one up and one down. And so anytime you see a double bond, you got to take an extra minute and just go, okay, is it cis and trans? So, you know, if I draw a bunch of just random molecules, no matter how I draw them, you know, some of those are going to be cis and trans and some of those are not. And so we just kind of have to look at it and say, well, is it cis or trans? For instance, if I take a look at molecule number 1, is that a cis or a trans? Or neither? Really, I should point out there's a third option, neither. Yeah, this one turns out to be neither, because if I take a look at that end, those are the same, right? So we would just label this, what, 2,3-methyl-2-butene. What about the second one I drew? Yeah, that's a neither again, because again, that's the same. And so we would name that one 2-methyl-2-butene. What about the third one? Yeah, here, that's implying that there's a hydrogen and a hydrogen, right? So on each side I have a methyl and a hydrogen. That implies that they are different, and so this is trans 2-butene. What about the bottom one? This is actually neither, because again, you know, that and that are the same. And in fact, that's actually just this molecule drawn a different way to try to trick you into thinking it's cis or trans. So be aware, anytime you have a molecule with just a carbon-carbon double bond, it might be cis or trans. For instance, if I draw this, I'll bet you the first time I named it, I didn't bother putting the cis or trans in, but that really is 1, 2, 3, 4, 5, 6, 7. That really should be trans 3-heptene. Because I draw most of my molecules as zigzags, that means if I'm not paying attention, I generally draw the trans isomer versus the cis isomer, right? And I also should point out, this cis-trans stuff will come back and bite you in the butt a little bit, in that we'll talk about cis and trans fatty acids, and so you need to remember what the cis and the trans mean all the way from this chapter. And because if I draw the hydrogens in there, this is implying that this hydrogen is down, whereas that hydrogen is up. So by drawing it as a zigzag, we automatically imply trans. If I wanted to draw it as the cis isomer, let's see, 1, 2, 3, I have to draw a little flat piece and go like that. And it really does put a kink in the molecule. In fact, maybe I should get these out and draw some bigger molecules, and you can see how it actually kinks the molecules. And so this would be the cis 3-heptene. Now, I don't really want to overload you guys, because we're going to learn how to name aromatics next. They've got their own separate set of rules. And then we're going to start going into the chemical reactions for these, and there's a new set of rules and stuff. So maybe I'll just cover one more short little topic since we have time. And that's, let's look at the bonding in carbon-carbon single bonds versus double bonds versus triple bonds. The first thing we noted is that these are capable of free rotation, whereas these are not, or they're fixed. And we note that if I have just a carbon-carbon single bond in a molecule, if I draw the rest of the parts in, what shape does that make around each carbon? That's tetrahedral, and it's 109.5. If I draw the double bond, and notice that when I draw these, I certainly don't have to draw them kind of emphasizing the angles, but if I'm being really good, I do, and that's trigonal planar. That's a 120. And then if I draw a triple bond, that actually gives me a linear molecule. It's 180 degrees. And then there's one little piece of tricky stuff I want to cover. It's ugly. I don't tend to ask very many questions on the test, but I would like you to make an effort at understanding it. And the reason I say it's tricky is because it makes us go all the way back to chapter 10. Do you guys remember what was in chapter 10? Yeah, that's literally last year, although honestly only about 2 months ago. So chapter 10 used S and P orbitals. You guys remember those a little bit? And you remember when we drew the energy level diagrams? For instance, we said, you know, here's my 1s level, then my 2s level is higher in energy, and then the 2p electrons are even higher in energy like that. Now we're going to ignore the 1s electrons, because if I take a look at carbon, that's 1s2, 2s2, 2p2, right? It has 4 valence electrons, and so these are the ones that are involved in bonding. These are our valence electrons. They're the ones that can form bonds. And what that's really saying is that if I kind of looked at my carbon, here's my 1s orbital, right? And then further out, I've got a 2s orbital with some electrons in it. And then remember, the p orbitals look like dumbbells. And so I would have an electron in one p orbital, I would have an electron in another p orbital, and then I would have an empty p orbital. And remember, it's only those electrons that are furthest away from the nucleus that can form the bonds, right? Meaning the electrons on the inside, you would have 2 sets of electron clouds. And what do we know about electrons and electrons? They repel each other, right? And so those inner electrons, you can't get them close enough to form bonds. You can't get them close enough to be attracted to the other nucleus. And so you get something like that. Now, when we draw these pictures, like I said, we tend to ignore the 1s electron, and we just look at 2s and the 2p's. So if I kind of just skip to that and say, here's my 2s, here's my 2p orbitals, and then if I draw those electrons in, that's what a carbon looks like, right? Does that make sense? And so if I take a look at methane, that's got a carbon atom, right? So I'm just going to draw my carbon. Well, in my 2s orbital, I've got 2 electrons, right? And then in one of my p orbitals, I've got an electron, right? And if I take a look and draw a hydrogen atom there, what type of orbitals does a hydrogen atom have? Just a 1s, right? And so it's got an electron there. And so if I take a look at it, that means I can form a carbon-hydrogen bond. Remember, that's my shared electrons. And so our shared electrons are kind of like that overlap between the p and the s orbital. Does that make a little bit of sense or not? I should also point out that if you don't like my drawings, and I really urge you to open your book up for this one and take a look at the pictures. This starts on like page 507. It's the very beginning of chapter 20. It actually comes before how to even name compounds, but I kind of wanted to do that first to make sure we got it done. That their pictures are 10 million times better than my pictures because they are color, they can draw 3 dimensions a little bit better, and things like that. Now, I've also got another p orbital, right? And so I could draw another hydrogen overlapping it. And so that means I really can draw this part of the molecule. But what about the other 2 bonds that we know carbon should make? Aren't those electrons trapped in that s orbital? So the first thing we need to do, because we know carbon makes 4 bonds, right? I mean, that's just like a fact of life, is we take an electron from an s orbital and we move it up to the p orbital. And that's called promotion. And the idea being that it takes a little bit of energy and we promote it from a lower level to a higher level. Just like in the Army, if you promoted someone from a low level to a high level. And so what that really does is that changes our picture to look something like this. Here's my 2s, here's my 2p. Now I've got 4 different bonds I can make, right? Meaning if I take a look at that carbon, and one of the hydrogens, that's a 2s and a 1s. If I've got a carbon and the other hydrogen, those are all 2p's and a 1s. The overlap of a 2p and a 1s. Oops, the 2p is on the carbon. And up here we've got a 1s and a 2p overlap. Or if I try to draw that in 3 dimensions, I've got one carbon-hydrogen bond like this. That's an S and an S overlap. And then all my other ones look like this, where the overlap is between a P and an S orbital, right? And then I've got another P and an S orbital. And then I've got another P and an S orbital. So what I really get is I get a CH4 molecule that has 3 of the same bonds and 1 of a different type of bond. And so what we're saying is that one of the bonds in methane, in CH4, should be a little bit different than the other 3 bonds because of the difference in overlap in the orbitals between P and S orbitals. But experimentally, not experimentally, we know that they're all the same, that they react exactly the same, that if we do a bunch of different spectroscopy techniques on them, they react the same. There's absolutely no evidence that those models or that those orbitals are different. And so we introduce one more complication. And the reason I want to introduce this is because it physically describes what a carbon-carbon double bond and triple bond are eventually, and it explains why they're much more reactive than carbon-carbon single bonds. And so if you can follow this logic around and answer maybe a test question on it, then that's awesome. If you can't, the take-home message is simply going to be the end part that I'll tell you, that that's the key. So we need to do one more thing. We need to take our picture that started like this. Oops. And what we did is we promoted. And so we got something that looked like this, where I've got 4 separate electrons. So this is the 2s and the 2p, 2s and 2p. And we do one more step. It's called hybridization. When I talk about hybrids, what do you guys think of? You know, that's pretty good, because normally when I think of hybrids, I think of Mendelevian genetics and, you know, crossing different strains of plants to get their things together. But this works pretty good too for hybridization, because a Prius is a hybrid between a gas engine and an electric, right? And so it's taking 2 different things and it's kind of putting them on the same level. Well, the same thing here, what we consider hybridization is if I take and make something called sp3 orbitals, meaning I cross an s orbital and 3p orbitals. And you have to remember also that, remember, these orbitals are actually waves, right? Remember that whole wave-particle duality? And so what I like to think about hybridized orbitals are they're just kind of like music with more than one note. Meaning that I can combine 2 waves together, or 2 notes on a guitar together, and get something that sounds different than just a single note, right? So I can literally mix those waves together. Or if you want to think about it in terms of colors, it's kind of like saying I take red plus 3 blues, and what does red and blue make? Purple. And so I get 4 purple orbitals, meaning I can kind of think about that mixing as being a physical process with waves and tones, or I can even think about it in terms of colors, where I know that I can take separate and distinct colors and mix them together to get a new color. And so what we're saying is that by mixing them together, now I get 4 orbitals that are exactly the same. Therefore, I make 4 bonds that are the same. And the nice thing about this theory is it predicts that these 4 orbitals have a tetrahedral shape. And what do we know about carbon with 4 bonds? It has a tetrahedral shape. This is sometimes called valence bond theory, the overlapping of these valence orbitals. And so if I have an s plus 3 p orbitals, I get that sp3 hybridization, and this is my best bet to what a tetrahedron looks like. It looks like it's tetrahedral. If I take an s and I get 4 identical orbitals. If I take an s and only 2 p orbitals, meaning kind of like I take and only mix 3 musical notes together, or I only mix red and 2 blues together or something, I get what's called an sp2 hybrid orbital. And what that looks like, and here's where my drawing skills are tough. Let's see if I can sketch a 3-dimensional axis and give you a little bit better idea. We get one orbital that looks like that. We get 2 orbitals that are at 120 degrees. And so here's my sp2 orbitals. And because I have a leftover p orbital, I get a p orbital that's up and down. So there's my leftover p orbital. And so what that means is that I get 3 identical orbitals and 1 orbital that's different. Does that kind of make sense? You almost have to draw the pictures. You almost have to kind of walk yourself through it. And I've got models, but they locked, and I have no idea where the key is. I'll pull those out tomorrow probably, and we'll do that. And so what that means is that if I take a look at the bonding in something like that, wait a second. I love this part of the lecture. Any day, it doesn't matter what day I give this. If it's a Monday, Wednesday, Friday, if I fed you so much caffeine that you were bouncing off the walls, I don't know. This is hard. It's hard to picture. It's hard to think about. You almost have to read through the book and look at the pictures and hear it more than once, meaning I really recommend reading outside of class. Read the beginning of chapter 20, and then actually they throw the SP3 part at the beginning of chapter 19, I think. How many people have read your book? Where do they throw that in there? Maybe they don't do it very well. Well, remember, there's always an s and 3 p orbitals. That's from quantum mechanics, right? And so if I mix an s and 2 p's, that means there's got to be a leftover p orbital. Because there's got to be 4, right? And so what that does is if I make a molecule that looks like this, so here's a carbon atom, and here's a carbon atom. There's an sp2 overlap. Okay, meaning, can you picture 2 of them being brought close together, right? And then for the other orbitals, I've got an sp2 here and an sp2 here. I'm just going to put those with hydrogens. Mostly because hydrogens are easy to draw. They're just that. And so these are sp2s and an s orbital from the hydrogen. Does that make sense? And then remember that last orbital goes up and down like that. And so what happens is, and it's really always hard to draw, these can actually overlap. And so this is a p-p overlap from that leftover p orbital. And really, if I were really drawing it right, meaning I was really kind of drawing it to scale, those p orbitals are actually big and fat. And so there's an overlap on the bottom, and there's an overlap on the top. And so this overlap here represents one shared pair of electrons. And so what that's really saying is that if I take a look at this molecule right here, that one of these carbon-carbon double bonds is an sp2-sp2 overlap. And the other carbon-carbon double bond is between a p orbital and a p orbital. And what that's going to mean is that one bond in carbon-carbon double bonds reacts kind of like a single bond, and one bond in the carbon-carbon double bond reacts completely differently. And so just by adding a double bond to a molecule, we radically change the type of reactions that it can undergo and what happens. And this is called sigma overlap. And if you notice, that sigma part is between the atoms. This pp overlap is called a pi bond or pi overlap. And notice that the electrons are above and below the atom. And so what I'm trying to say is that there's a difference if the electrons right here are between the two atoms, and here where those electrons are above and below. Now this is hard, and you know, a certain part of me says I've actually in the past have skipped it entirely, but I think it's worth covering at least basically, you know, at a basic level, or at least going through it once. If nothing else, the message I want you to take home is the following. A carbon-carbon double bond has one sigma and one pi bond. And so the carbon-carbon double bond acts like a single bond. One of them looks like a normal carbon-carbon single bond. The other one has that electron density way above and way below the plane of the atom, and those electrons are very exposed. And what that means is that a carbon-carbon double bond is really reactive. You noticed that in lab when you did the bromine test. The carbon-carbon double bond reacted immediately, right? And the carbon-carbon single bond took either 10 minutes or you probably had to expose it to UV light. You also noticed it when you did the reaction with that potassium permanganate. That was the purple stuff, right? The carbon-carbon single bonds didn't react, did they? But the carbon-carbon double bond can react with that potassium permanganate because those electrons are exposed. And so that's my big take-home message. Know the difference between sigma and pi, that the overlap is above and below the plane of the atom, so it's exposed. Pi bonds are very reactive. Sigma bonds, where the electrons are between two atoms, tend to be very non-reactive. And so one of the things that we should notice going forward is that every time I draw a carbon-carbon or a carbon-oxygen or anything with a double or triple bond, that's the part of the molecule that reacts. The rest of the whole rest of the molecule is pretty stable compared to that. Aaron.
So the pi overlap is like on the right up there is just where they overlap, and then the what's that side?
So the sigma overlap is this. Notice that it's between these two electrons, right? Sometimes it's called head-to-head because it's like two things overlapping. Here, because this is the overlap is above and below it, that means that the electrons are further away from the nucleus. They're not trapped between the two protons, right? That means that because the electrons are way out here as opposed to stuck between them, they're really reactive. And the whole sigma pi thing, I don't know if there's a real reason or if they just arbitrarily picked sigma and pi to describe that. I'd have to Google that and see why they're called sigma and pi. I think they're just names like A, B, personally. So realize that carbon-carbon double bonds are very reactive. In fact, this picture of what a double bond looks like is not quite right, because one of the bonds really should only be between the two blacks, right? And then one of the bonds really has actually two parts. Half the electron is above it and half the electron that's being shared is below it. And those are the ones that are really reactive, that it's very easy to get something in there to react with it. If you guys want, I'm going to stop the recording and let's just go out and see if we can open the cabinet.